So I will start with illustrating it with embedding of LP, small LP, or integers. So with the norm x k, so it's the norm. This is sum of x k to the power p. So maybe this way is better?
Yeah.
Okay. So x k to the power p1 over p, k from minus infinity to infinity. And L infinity, so this will take this p less than infinity. So x infinity is, of course, prime of k over k, and there is obvious continuous embedding of LP into L infinity. So the continuity is guaranteed because surely the smallest element is, so largest element is less than also. So at the same time, this embedding all very clearly not compact. So if we take a standard basis, so in k, so this is 0, 0, 1 application is 0, 0. So it converges weakly to 0 in LP. And of course, if embedding were compact, it would mean that its largest component will also go to 0, but it does not. So what very obviously stands in the way of compactness is the presence of translation invariance. So the norm is translation invariant with respect to the actions. And the question that one asked is, well, so right, it does not imply EK converges to 0. So maybe one can strengthen this condition somehow, accounting for translation invariance, so that the implication will be still true. Of course, not for this sequence, but for some other sequence. And the idea is to use the translations. So let's denote TL applied to the vector x as, let's say, right shift. So so the k component of it will be xk minus 1. And let us require that the sequence xk is such that t for every lk in Z, t lk xk will converge weakly to 0. So instead of simply assuming weak convergence, we will be able to translate the component and intuitively speaking, to run after the largest component with our operator, always keeping the direct bit and make it go to 0. This is much better. So this is much better because literally in LP there is the largest component by modulus, and so we can always, for any sequence, shift it exactly to the value to the largest value. So this immediately implies that xk converges. Just a second, I abuse the notations. So no, it's okay, except for the notation component should be here. So xk will converge to 0 uniformly. So bear in mind that weak convergence in LP space implies convergence by components, and so this means that any sequence of selected components for every term of the sequence will go to 0, including the largest one, so we go to 0. So this property we generalize into a functional analytic definition and call it co-compactness. So suppose that we have D group of bijective isometries, linear isometries X, and we say that xk converges D weakly to X if for every sequence gk in D, gkx k converges weakly. Gkx k minus x converges weakly to 0. So one can try to visualize this situation pretending that the sequence is actually a flock of sheep. So each peak value on the sequence is that might be traveling with the index k. Every such peak has to be tracked down by translation and brought down so that you will have any chance of getting the sequence converted to the target space. So I will return to this sheep metaphor later. But for the moment, I want to show on less artificial examples which embeddings are co-compact and what follows from them. So for the moment, what we have proved is that if D is a group of shifts on LP, P less than infinity, then LP is D co-compactly embedded into L infinity. So the definition is an embedding X into Y is D co-compact if xk convergent D weakly to 0 and X implies no xk and Y converges to 0. So in this setting, co-compactness is just a generalization of sequential compactness. So if the group D consists only of identity operator, then what is written here is plain weak convergence. No shifts are undertaken. And the weak convergence in X implies non-convergence in Y's compactness of embedding. So co-compactness is requires weaker is a weaker property. It requires much stronger convergence in X to which it is. So the first analytic example in the real spaces that I will take up is Sobolev embedding. So I will take embedding of W1P of Rn, which we have talked about so many times already, into LQ Rn. So Q will be, I'm interested in values Q strictly less than P, strictly greater than P, and strictly less than P star, which is P n minus P, and we assume that n is greater than P. So, so the theorem, this embedding is, so this embedding is, it's of course not compact. So to start with, why it is not compact, take any fixed function, translated with yk going to infinity. This sequence, let's call it wk, this sequence goes weakly to 0. At the same time, w0 to the power p, translated or not, is a constant with respect to k, and there is, of course, no compact embedding. So we immediately see that translation invariance is a usual culprit for loss of compactness. So now the theorem, this embedding is co-compact relative to z and h's. So we'll call it g alpha. U of x is u of x minus alpha in. So this theorem is actually due to Elliott-Lib, 1983, but of course he didn't use this terminology, and he stayed in slightly less general form. So it's known for people who didn't bother with the functional analytic version of this theory. It's known as the deep vanishing lemma. So let me give a short proof of it. So I think the simplified proof is due to Michel Delem. It was produced 3 years later. So the proof goes like this. Take a cube. So let q be 0, 1 to the power n. Take a cube and write the Sobolev embedding on exactly this embedding in restriction to the cube. I mean, not exactly the same in the version of the embedding for a cube. So u to the power q is brackets is later just equal and a constant gradient u to the power p over the cube. So now the homogeneity is not matched, so we will compensate it by putting u to the power q to the power 1 minus p over q. Okay, now if you collect the terms, you will get power p over q. Homogeneity is fine. Now the statement is correct. Okay, so nobody will doubt this inequality. So I will start the proof a little bit earlier, saying let uk of dot minus alpha k converge weakly to 0 for every sequence alpha k of integers alpha k. So let us write it for our terms of the sequence k, and let us add to it shift alpha. So the problem is translation invariant. We can write it over every cube, and then let us add up terms on the left and on the right. So when we add them, you get a distillation of the whole space, and you get uk to the power q over Rn, less or equal to the constant, and this I will simply take by maximum. So supremum over alpha in the n, integral of uk to the power q to the power over q plus alpha 1 minus p over q. And after I have taken the supremum, this I add up these terms, which give, and of course I wrote an ugly mistake, that the statement would be false without p terms. So after we add them up, we get simply u 1p norm to the power p, okay, which is by Banach-Steinhaus is bounded. And so the question is, what happens with this term? Well, So within this term, we quote local compactness, or compactness of the local subgroup embedding. So if so I will write. First of all, I will take alpha k such that q plus alpha k q to the power q is almost supremum. Let's say that the greater or equal than 1/2 of this. K to the power q. So then let us change the variable and rewrite it as uk of dot minus alpha k to the power q or q. And here we quote our condition and compactness of local subgroup embedding. So this guy goes to 0 in W1. Therefore, it goes to 0 in LQ. Therefore, this term goes to 0. Therefore, the supremum goes to 0. And therefore, the right hand side goes to 0. And we got conversions to 0 in LQ. So co-compactness is So, few words of history. So, historically, this kind of reasoning is called concentration compactness, and this is to do to another mechanism that involves in loss of compactness and is dilations. And also is to do with history. So, the people who introduced this method as a staple of analysis, so Karin Uhlenbeck, Nick Pierre Louis Lyons. Let's arrange 82 to 85 from his first note on the topic to 4-paper series. This Lieb, Nirenberg, Coron. So also 82, 84, and Struve. Also about 84. Most of this work was dealing with the more challenging problem of loss of compactness because of scale invariance, and they were putting things in terms of weak limits of measures of Lagrangians. What I'm going to speak about is a version that is more suitable for functional analysis. It is set for abstract spaces, not for spaces of functions, and however, the output is such that in functional spaces it allows to translate everything back to measures, as I might show later. So, this explains the difference of terminology, co-compactness versus concentration compactness. So, let me immediately show how co-compactness of embedding can be put to work. So an application that I want to show is the classical Strauss lemma, or lemma of radial compactness. And be called theorem, in fact. So Strauss plus anti-theorem. So let W1 be our radial of Rn, be the subspace of radial symmetric functions. Q is between P and P star, so we assume n greater than P, then W1 of P radial of Rn is embedded into a Q of Rn compact. So the main tool in proving this lemma is another famous analytic statement known as Brézis-Lieb lemma, which is a nice improvement of Fatou lemma or weak oversimplification property of a norm. So let me quote Brézis-Lieb lemma. So we have omega nu measure space. We have P between 1 and infinity, UK convergence weakly to U, and UK of X convergent to U of X for almost x. Then integral of UK squared is, so I will first write what denotes. I will first write what does it say for Fatou lemma. Fatou lemma would give that this is greater or equal than U squared d nu plus O of 1. But the improvement is that in fact you can write explicitly the defect of convergence here, and two is of course correct, but I'm interested in Q, so let me change the notation to Q to coordinate with that, and here we are. There is one dramatic observation that you don't need convergence almost everywhere when Q equals 2. But this is the defect of weak convergence that we are going to use in the proof of Strauss lemma, and let's get to the proof of Strauss. So assume that there exists a sequence alpha k in Rn. So of course, okay, I will make a comment later. The sequence such that no, I always start the theorem from the proof from the middle. So let UK converge weakly to 0. This will be enough without loss of generality. So in W1 radial, we want to show that UK converges to 0 in LQ. Suffices to show that for every sequence alpha k in Zn, and even better if you prove it for all Rn, UK of dot minus alpha k will go to 0. However, UK is already a symmetric function. So if we replace its argument by the rotated argument, so that omega be an element of O of n, then UK of dot minus omega alpha k will also go weakly to 0 for every omega. And then I claim, by virtue of Brézis-Lieb lemma, as we shall see, that just a second. I don't want to assume that. Let me see what I want. Okay, so I put here a period, and again I would rather start differently. So let assume this is not true. So in some sequence, let alpha k go into infinity. So alpha k bounded are not interesting here because it's the same as fixed shift. Let's alpha k go into infinity. Be such that uk of dot minus alpha k converges weakly to some v, which is not. Let's call it u. Then we have uk of dot minus omega alpha k convergent to u composed of omega minus 1. I hope. So in any case, we can apply this Lie lemma and get that uk to the power p, which is of course the norm of this guy as well, is greater or equal than uk dot minus omega alpha k minus u to the power p plus u to the power p. But now we can iterate, because this sequence we can again apply to it another rotation, and another rotation will produce another limit going here. So if we are getting a limit on the sequence that sits here, by rotation we get a limit that peaks here, and their supports are asymptotically divergent, so I don't want to get into detail. So what we get, in fact, is because there can be infinitely many terms, we get by iteration that uk to the power p is greater or equal than mu to the power p for any m plus all of 1. And this is, of course, a contradiction because we started with bounded sequence. So, so the moral of the lemma is that because we have a group that allows us to reproduce multiple copies of the sequence translated and running into separate directions, this simply is not allowed to happen. If it doesn't allow it to happen, the sequence will converge weakly to will converge to zero under any sequence of translations, and by co-compactness it means that it will converge in the target space. So we have proved Strauss lemma. So what I want to show now is how does Strauss lemma work in a geometric situation. So first of all, co-compactness. So we'll have a complete Riemannian manifold. And so isometry of M, it's a isometry group. And the set D will be the set of group shifts. So it's the set of mappings U to U composed with eta in isometry. A group of actions of isometries. So the theorem, which is in fact a clone of the Lip's theorem, says the following, that if, and I will leave space for the condition for the moment, then, I'm sorry. I'm in the middle of a family emergency, so I might get some call that, so if the condition I will spell out, then W1D of M is D co-compact can be compactly embedded into it. So the condition is, of course, as before, P between Q, between P and P star. And the other condition is that as is M is co-compact with respect to its isometries. So, which means that there exists a compact set, subset of M, such that union of eta k, eta and isometries M is equal to M. So one can think about Rn. So you take a unit square, you translate it by arbitrary vectors to cover, of course, the whole plane. Or you can think about an egg carton that you translate each hole into another hole by lattice translations. So, so the word co-compact is used here in two different cases. So co-compactness of isometries leads to co-compactness of entropy. So the proof of this statement is a repetition of the proof in the Euclidean case, except for there is no immediate tesselation, so one either have to construct a fancy tessellation, which I think is possible, but I never bothered to check it, or get a suitable covering lemma, which is more or less known, so we can take this for granted. So with knowing the co-compactness with respect to isometries, we can state an analog of the Strauss radial lemma. So let omega be a subgroup of isometries. And so I think about a group of orthogonal rotations in Rn as an example. And let W1p omega of M be the set of U in W1p of M such that U composed with omega. So I'll assume that W1p into LQ, Q between P and star is D co-compact. Then the embedding W1p omega M into LQ M is compact if and only if the following geometric condition holds. So here I will draw a picture. So think about an orthogonal group of n-1 in a problem with a cylindrical symmetry. So so this group will have an orbit that in the remaining direction can be located everywhere. So this is a situation when we will not get a compact embedding, and it can be characterized by having orbits of bounded diameter at any distance away. So they're not compiled. So orbits of diameter less than r are not confined to any bounded region. So what we are going to ask is the opposite. So we take the set of the orbit omega x and measure its diameter, and consider all those points such that this diameter is less or equal than t. So let's call this set MT. if the set MT given by the formula is bounded for every equation. So reference is myself and Leszek Skripczak. So 2013, I think, mathematical. So this is my revenge for my difficulty remembering Indian names. I still didn't find anybody here at the institute who could reproduce this name. So. Okay, about the proof. So I give on the sketch of the proof. It's again mimics the proof of the Strauss lemma. So if you have a sequence, you want to show that any sequence of isometries applied to it will go weakly to zero. So we're interested particularly in isometries that are not compact, that are discrete, that takes points at arbitrary outside of any compact set. If you assume that there is some weak limit, you immediately rotate it with omega, and this property assures that you will get a lot of copies of the same function rotated by the set omega, which will blow up the norm, which will contradict to the precisely lemma. And conversely, why this condition is necessary, because if you are able to produce those orbits of bounded diameter that stay very far, we can assure that they will be disjoint. We will build solutions supported in the vicinity of those orbits with disjoint supports. And by taking a sequence, by moving by isometry from here to here to here to here, we will construct a non-compact sequence. So that is how co-compactness is one of examples of how co-compactness works in the case where it is basically translations. Translations are actually isometries that act very similar. So this extends, by the way, from Riemannian manifolds to sub-Riemannian manifolds. So basically, we are using only the basic properties of isometries. We are not using Riemannian structure as such anywhere. So on Lie groups, etc., etc. So our next step will be to look at a different group, and this is the group of deletions. Now I will limit myself to the space D1 to Rn, so I could write D1P. So this is for n greater than 2, and this is the functions with the gradient norm. Alright. And here we have the sharp Sobolev embedding, so D1 to Rn is compactly embedded, continuously embedded into L. So not only this embedding is not compact for the previous reason, which was that one can translate the sequence to infinity, get sequence weakly conversion to zero, but with a constant bulk here and here. But there is another transformation, that scaling transformation, that also preserves the norms, but creates sequences that go weakly to zero. And this is transformation tk, so I'll take sequence tk n minus 2 over 2 u of tk dot. So this will go weakly to zero if tk is, so tk is positive number, if tk is going to zero, or tk is going to infinity. When it goes to zero, we are getting something that looks like delta function, so very little support and very tall function. So obviously, if you integrate it with a test function, it will go to zero. If you reverse and send tk to infinity, you will get something very flat. So if you integrate on a complex support, it will go to zero as well. So we get big conversions to zero as a result of the scale. So this embedding is not compact, and it is not co-compact with respect to translations either, just because translations don't help loss of compactness with regard to scale. So if you have a peak like this, you translate it, it still remains a peak like this, it still remains, no matter how you translate it, will weakly go to zero without changing the norm. So one has to incorporate this property. Theorem, and I think the oldest reference is Leon's 84. So if for every sequence of tk greater than 0 and y alpha k in Rn, uk renormalized, rescaled, and translated goes to 0, then in D12. Then it goes to 0 in L star norm. So there was some embarrassing time when the Onsis proof was the only proof, and it was long proof, and he left out a lot of obvious statements that nobody liked. But several other people participated in cleaning it. So Ben, I think, has some reasoning, and so by now there are 5 or 6 very clean textbook quality proofs of the statement. So I will give a hint how to do it, just because the group is rather large. Calculations are not so much useless as they're bulky. So I will take the case of D12 radial, and in this case it's enough to use dilations only. The relations into L2 star, so which means that if for every sequence tk n minus 2 over 2 uk of tk goes to 0 and uk is radial, then uk goes to 0 in L2 star. So the trick is very simple, partition of range. So if co-compactness for translations 1, if co-compactness for the translations 1 verifies by making a distillation of Rn, here we do dyadic translation, dyadic partition of the positive axis. We can take as a cutoff function something like this. You don't have to do a one distribution of unity. It's enough to take something like this. Define the similarity. So you take here 1, 2, 4, and 1/2, and take a function like this. And then define chi j as 2 to the power j j chi 0 of 2 to the power minus j t. And this will highlight a window between 2 to the power j and 2 to the power j plus 1. And then one writes Sobolev inequality for these functions. And because they are bounded functions, there is bounded radial functions. One can call Strauss lemma to claim compactness. And then one rescales, one puts together pieces exactly like one did it with partition of domain, and so ends up by estimating uk to the power 2 star as constant of uk, let's say 1, uk, so self-creates uk 2 star times the norm, gradient norm k squared. Okay, here exponent I don't can calculate k between 1 and 2. Translated, dilated. So because under any dilations, so one can put here any exponent because it's function bounded and bounded away from 0. Sorry, just bounded. So in any case, this is roughly the argument. How does one get co-compactness in this case? So the key word is find a smaller piece of a function, find a partition of function into pieces where embedding is compact, and then use convexity argument to assemble the pieces together. So again, a large conformal group from the manifold that involves just relations with scalars are a rare thing, but on Lie groups they come very easily, so there is an immediate analog of this embedding also for Lie group. So the issue with concentration, however, is not finished, because what one wants to get at the end is convergent sequences in the target space. And of course, a statement. So Banach-Halog theorem says that if X is reflexive and UK is bounded, then UKJ converges with this to 0 some J. So if there is a compact embedding, this will imply that the norm of the target space will get convergence. Now suppose that we don't have compactness, but we have co-compactness. So one is tempted to ask, well, what then? Can we say that any bounded sequence has a d-weakly convergent subsequence? The answer is, of course, no. No, for a very simple reason. So take a bounded sequence w dot minus yk going to 0. It is not d-weakly convergent, and none of its subsequences is d-weakly convergent. It is a sequence that will diverge in LP, so one cannot use co-compactness, invoke co-compactness in making the sequence converge. It does not, and that's it. So the correct statement is what is more or less, after many haggling, people agreed to call profile decomposition. So this is my last talk for today. So, theorem. So I will fill it from the parts. So every sequence. So okay, let X be a reflexive. Let UK sequence. Then there is a subsequence, renamed subsequence. Such that, so I will add here immediately x co-compact embedded into some y, such that uk converges converges to 0. So the statement is, however, that UK does not itself converge to 0 in y. So UK will converge if you subtract so-called profiles or elementary concentrations. So there is the sum, okay, from 1 to n from 1 to infinity of g, k, n, w, n. So that if you, so there is a countable set of blow-ups, maybe we'll call them elementary blow-ups. And so GKN are elements of group D. So if you subtract all blow-ups, then the remainder will already go nicely to 0 in the Riemann space. So this is general profile decomposition on the functional analytic level. On the second lecture, I will cover less known examples of groups that have this effect, and these groups come from the two-dimensional modeling work. But here I want to put in missing conditions, so there is plenty still missing conditions in this theory.
What are these elementary blocks?
So any term of the form, transformations times a fixed function is, in this context, we call it elementary blow-up. So group D is an absolute group. If this group is responsible for co-compactness, then under a couple of extra conditions, one can express the defective convergence as a sum of terms that are being distorted by them. So, like translations in the subcritical case, like rescalings that involve dilations in the critical case, like quite a few other things in other situations. So, let me put extra conditions. So I want the norm not only reflexive but strictly convex. And smooth. So it's a property, both strict convexity and smoothness is property of the norm. Then the group D will be required to satisfy some condition. So the condition will be a little bit strange. So GK is in D, GK does not weakly converge to 0, then there exists a subsequence such that GKJ converges strongly to some G in D. So strongly means G for every X, GX converges to GX. So I will explain this condition in more detail, but let me at least illustrate somehow it's satisfied in all applications. So if you think about translations, going weakly to 0 for translations means that the translation vectors are going to infinity. So if they are not going to infinity, there is a bounded subsequence. A bounded subsequence has a convergent subsequence. Correspondent shift operators will be strongly convergent. Same thing with relations. Either the scale is going to infinity or to zero, and then we have weak convergence to zero, or it doesn't, and then the scale converges to some limit points on the subsequence, and we again have this behavior. So same with isometries. Isometries converge to isometries because of the scholars allies equivalent to convergence of their value at one point. So we again verification of this property ends up with Boltzmann versions. So let me see if so the conditions are now set. So one only has to add the assertions. So in fact, one has the following: there exist sequences of dislocations, we can call them, these distorting operators, and Wn, which are in fact weak limits of GKN minus 1, GKN minus 1 UK. After subsequence we can reach it. And what is more interesting is that GKN inverse GKM converge weakly to zero whenever m is different from n. So this corresponds to our transformations to be asymptotically orthogonal, or to live on incompatible scales. So it can be, so this incompatible scales might mean that we have translations that are running away from each other, or that we have translations that are not running away from each other, but we have dilations onto relatively separate scales, so their contribution to all integrals will be separate. So we have on the functional analytic level the separateness condition for this profiles. So which bodes very well for energy estimates. Finally, in what sense this yes, so for convenience, W1 is just weak limit of UK, so you can start source looking where does UK itself converge in the subsequence, so this we call W1. And so what pieces we still have to add? Yes, convergence of the series. So the series converges just in X uniform in K, and if UK is less or equal, the norm for K is less or equal than 1 in X, then the sum of the moduli of convergence of moduli of convexity versus the moduli of convexity of the profiles is less than norm of K. So this is modulus convexity. For Hilbert space, so if x equals h, we have simply sum of W and squared less or equal Okay, so now the theorem is almost stated. So the Hilbert space version of this theorem we have proved in around year 2000. It took us 6 rejections from the papers to get it published. So it got published, we immediately were handed me and Ian Schindler. So we immediately handed book contract and I wrote with another co-author a rather sloppy book motivating the whole business. So the book is 2007 World Imperial Pledge Press. Then it took us 10 years to find a missing condition for Banach spaces. So the condition is still not written here. I think I need one more color, which will be pink, satisfying strong OPL's condition. So I have exactly 10 minutes to add up to the story. So for 10 years, I didn't know what to do, how to get to the result, because obviously something was missing. We were completely baffled by the missing condition. So there were very few people who were involved in formulating profiling compositions. So I have to credit, first of all, Sergio Salimini. So 1995. I should start, of course, from Struve in 1984. Struve 84, but his profiling composition was for policeman sequences for elliptic operators. It was not for the general case. The ones produced his versions in 86, also policeman. Benchicirami did both unbounded domains and critical exponents. I think it's 92. Still only policeman sequences. Unprejudiced. So all for Sobolev spaces. So Salimini has written forced profiling composition. So the life is easier for policeman sequences because in all their problems there was a minimal norm of the profile, and so the sums here were always finite. And this saves a lot of headache and argument. But for general sequence, you cannot, of course, postulate that such sum will be finite. You can just take a sequence with these properties. It will have just these profiles and no better behavioral spectrum comparisons. So Salimini did it for general Sobolev spaces. In 98, 99, there came a paper with subsequent generalizations by Patrick Girard, followed by Stéphane Jaffar, who used wavelet arguments to get a profiling composition. So they reproduced Salimini's result without knowing, or at least without quoting him, and with a weaker form remainder. So unfortunately, it is this work that became known. Salimini got very few citations. So after that many years, simply wrote to Salimini and said, we have to fix it. He was very happy that somebody remembered that he has done the pioneering work, and finally we came up with this result, still not published, and the Opel condition. So the Opel condition comes from fixed point theory, and it is a condition of the norm in the Banach space that says that if UK weakly converges to U, then for every V in X, the lim inf of the norm UK minus U is less or equal than V inf of UK minus U. So if one combines it, however, so this is Zhyslav Opial, another Polish work from I don't remember a year, but it was around 1970, plus or minus a couple of years. So one can use some sort of some version of Ekeland's theorem to replace it when we have duality mapping by the condition, and this we call stronger condition. If this is true, then UK duality map converges minus U, sorry, UK minus U. Duality, this is not a linear thing. UK minus U star converges weakly to 0 in X star for reflexive spaces. So I think if duality map is not unique, it's enough that there is a selection from the set value duality map. So in any case, this is very nice property, except for it is satisfied in every Hilbert space, it is satisfied in every LP, and it is not satisfied in LP capital. So it's not satisfied in Sobolev spaces as well. So what one does, one renorms. So because this is a property of a norm out of the space, the trick is to provide an equivalent norm in LP or W1P true for the norm defined by Littlewood-Pelly decomposition, by the Littlewood-Pelly theorem. So in fact, this observation was independently done by people around Terry Tower. So so I will end up with this story with the ship that I promised. So how do you prove propel decomposition? You have a sequence that you expect to consist of a sum of the bulks, each of them running away to infinity. So treat them as three ships. You send after them shepherd dogs, which are your transformations that bring your terms to the origin, and then you require them to sink weakly to 0. So after you have collected all the ship and managed the energy estimate, the norm estimate for the sum, the stability estimate, you are having the remainder that is going to 0 d weakly, and by co-compactness goes to 0 by the target space. So when I gave a talk with this ship metaphor at analysis seminar at UCLA in 2003, there was curiously staring at me Chinese guy in the audience that his face really lightened when I spoke about the ship. So this was Terry Tao, who grew up in Australia, for which ship is a national animal. So the metaphor of ships immediately broke in, and the story appeared without reference to ships, very strictly mathematically formulated in his blog. So it ended up with him doing concentration analysis for nonlinear Schrödinger equation. I will mention it on my next talk. So it is the Stricher's embedding related to Schrödinger equation that is co-compact. And he and his collaborators used the Littlewood theorem not only for this but also to proofs of co-compactness for Sobolev spaces. It immediately had implication also for Besseff and triple Zorkin spaces, but this is, I think, the time will end up the first part of the story.
Questions? What are you doing Friday?
What I'm doing?
Yeah. Next lecture.
So what I'm doing, so I will give a few more examples of concrete spaces where it works, and there are absolutely fascinating nonlinear, non-homogeneous dilations that govern compactness issues in Schrödinger motor. So one of the results that there are two amazing results that I will announce. One is the concentration profile for similar elliptic equations look like toy pyramids that many of us have played with when they were 3 years old. And another is that Schrödinger-Moser functional e to the power 4 pi squared integral on a unit ball where it is bounded is weakly continuous, basically on only one sequence. I mean, only on one sequence, module translations and modular remainder vanishing in subgroup norm. But so I'll show a very sharp result coming from profile decomposition that shows that one has to hit just in one sequence in order to get it.
This is a tower of bubbles.
No, this is a single bubble. The single bubble looks like a tower. So this is a perverse counterpart of the Lendy solution. Professor Chang has shown that if the nonlinearity is e to the power 2w, then there is a very nice counterpart. But if you treat as a Schrödinger-Moser nonlinearity this guy, then there is actually uncountably many Lendy solutions.
Okay, so thanks. Okay, so with this we will close today's session and we will reassemble tomorrow at 9:30.